Hello. Today we will discuss an application of the matroid algorithm that we had studied in the last lecture. Recall that we had described the problem which was given an edge weighted graph compute a minimum spanning tree. So we want to compute a spanning tree of a given graph whose cumulative edge weight is the least. Now let us first show that this problem can be converted into a matroid problem. So let us define a matroid as follows. So let M be this 3 tuple where E is the edge set of the graph, T is the subsets of E which we will describe in a minute, and W is the same weight function on the edges that was given in the graph. So where the members of T where for each T in T Vt is a forest. So every subset of E which along with the vertex set V forms a forest, that is how the script T has been defined. Now recall that a forest is any subgraph of our graph which has no cycle. So for example, if I have a let us take an example here. If this is my G, I am ignoring the weights right now, then some of the members of script T will be, if I label them as a E1, E2, E3, E4, E5, E6, E7, E8, E9, E10, then possible members are, for example, just E1. Maybe E1, E2, E8. There are many members. Notice that this one defines a graph containing this edge, and this edge. They do not form any cycle, hence they become a member of script T. Now we have defined all the 3 components of this M, and now our claim is that M is a matroid. Now recall that there are 2 properties that M should satisfy for it to be a matroid. So, first thing is the subset property is that if a T is a member of script T, T prime is a subset of T, then T prime should also be a member of script T. Now, first we notice that if T belongs to script T, then Vt is a forest. Now, suppose T prime is a subset of T. Well, then T prime also cannot have a cycle. The reason is that we have only deleted some of the edges from this graph, hence we cannot have cycle here, cannot have a cycle. Hence, Vt prime is also a forest. Thus, T prime also belongs to script T. The second property requires that if we have two members of T script T, namely T1 and T2, and T2 is not bigger than T1 in cardinality, and say there is some element E, there is some edge in T2 which is not in T1, then we need to show that there exists some edge E prime in T1 minus T2 such that T1 minus E prime union E belongs to script T. This is what we have to establish. So, let us say this forest, say T1 is symbolically this structure, and of course, there are vertices of V in this, and this is edge E which is not present in T1. So, E is not a member of the graph T1. Suppose we incorporate, we add this edge into T1, and let us suppose these are the two vertices A and B. If we deposit E inside this graph T1, then maybe a cycle is formed. But notice that without E there was no cycle in the graph. If at all a cycle is formed, if cycle is not formed, then by deleting any edge from T1 minus T2 will also keep it a forest, there is no harm. In case there is a cycle formed, then probably there is some path. These are the solid edges are members of T1, and now by putting E we have formed a cycle. In this case, suppose I delete any one of these edges, suppose we delete any one of these edges, call it say E, this is my E prime. Now I want to show that this again is free from any cycle. So let us suppose this is still a cycle. There is a cycle in T1 after incorporating E and deleting E prime. Suppose there is a cycle. In that case, that cycle must contain E in it, because without E anyway there was no cycle in the graph. So let us say more symbolically, here is my E prime, E. We have one path which contained E prime in it, and now even after this is deleted there is a cycle in it. So that cycle should pass, since it is supposed to pass through E, that cycle may have some part here, may go through this, may go out this way. In other words, that cycle may share some of the edges of the original cycle and may have some other edges outside it. And now what we have is this second cycle which does not require E prime. Now in that case, let us first of all visualize a simple situation where none of the edges of the second cycle are shared with the original cycle. In that case, it would have been simply E here, this would have been this way, this was E prime, and then there was a second cycle sharing no edge with this part, only the edge E, which was a new edge, shared. Then notice that in our T1 you already have a cycle which includes this, because this does not use E, therefore it is a cycle of T1. But that is not possible because our T1 is a forest, so it is not at all possible. So now we have to see if any edge is shared, what happens. General situation where the two paths share some of the edges. So let us say this is our new edge E, and let us suppose this was the original cycle with this being E prime. Now the other cycle that also contains E will begin from here and end here. Again we can visualize the same way. Now this cycle, when it begins, it may continue with the original cycle and then at some point it splits. Now starting from here we proceed until it hits the it shares the one of the vertices of this cycle. This vertex could very well be this vertex as well. So now the thing is, if we notice this particular portion is again a cycle, which is a cycle of T1, because all the edges that are involved belong to T1. Now of course if this vertex had been this one, then I would have had this as a cycle in T1 as well. Once again, this is not possible because our T1 is given to be a forest. Hence, it is not possible that after deleting E prime there is a cycle left. So we notice that T1 minus E prime union E is also a member of T, script T. Now we have found that both the conditions of a matroid are satisfied by M, hence M matroid. Now we want to know what are the maximal independent sets in this matroid. Okay. What are the maximal independent sets in M? Well, the maximal independent sets are those which have the maximum number of edges, those subsets. Now, if my graph G is connected, then any spanning tree of my graph is a member of script T. It is an independent set. Okay. So, let us get back to some observation. Observe that every spanning tree of the given graph VEW is a member of T. Now, here we are assuming that the graph is connected. Now, we claim that the spanning trees are maximal independent sets. Now, if they are not, then a spanning tree must be contained in another member of T. So, claim if VT is a spanning tree of the given graph, then T is a maximal independent set, a maximal set of script T. If this is not maximal, then this must be a proper subset of some member of script T. Okay. So, suppose, assume otherwise. Okay. Then there exists T prime in script T such that T is a subset but not equal of T prime. Therefore, there is at least one edge in T prime not present in T. Now, if you look at the graph corresponding to T, this is my T. Because it is a spanning tree, then there is a path between every pair of vertices in it. Now, suppose there is, and suppose E belongs to T prime minus T. So, let us say this is E, but T being a tree, a spanning tree, there is a path already present from this vertex to this vertex, and if I add edge E, then I am forming a cycle. If I am forming a cycle here, this no longer qualifies to be a member of script T, hence this is not possible. So, we conclude that this leads to a cycle. That means T prime does not belong to script T. This contradiction establishes that spanning trees are maximal members of the script T. Conversely, if there is a maximal member, so this shows that all spanning trees are maximal members. Now, conversely, we will now claim every maximal member is a spanning tree. Now, to prove this, we will use the fact that all the maximal independent sets have the same cardinality. So, now suppose we assume the contrary, assume the contrary. Now, suppose we have a member H of T which is a maximal set and it is not a spanning tree. If this is not a spanning tree, but it is still a member of this, then the one thing we can of course conclude is that the cardinality of H is equal to the cardinality of edges in a spanning tree which is of course mod V minus 1. Now, if this is not a spanning tree, then there must be at least two components in this graph. So, two component means that H may have at least two parts, maybe more. So, the entire H may be other parts. This is how H looks like. Then the number of vertices may be, let us suppose, n1, n2 and so on in each of the connected parts. Notice that by connected component means that there is no edge going from here to this, or there is no path from here to here, or from here to any other component. There is no edge going outside this, there is no edge going outside this, and so on. So, the sum of ni's is of course V, and the number of edges is mod V minus 1. So, in this case, let us suppose we have two components, say n1 is 2 and n2 is 3, and then there are 4 edges in it. If there are n1 minus 1 edges in this and n2 minus 1 edges in this, then this will add up to at least n1 plus n2 at most this much, my mistake. So, we have n1 minus 1 and n2 minus 1 edges at most in these, then this will add up to this, which is less than mod of V minus 1. So, in general, let us suppose in this picture, if the number of edges is at most n1 minus 1, at most n2 minus 1 and so on, then number of edges will be h will be some ni I going from 1 to k, there are k components minus k, which is strictly less than mod of v minus 1, because this is mod of v, the total number of vertices. Hence this is not possible, and so there must be at least one component, one connected component with ni vertices and at least ni edges. If there are ni vertices and ni edges, and if the graph is connected, then this cannot be a tree. Then this component must have a cycle, which implies that such a graph H must be a spanning tree. There is no other way out of it. So we have now concluded that every maximal member of script T is a spanning tree, and only spanning trees are the maximal independent sets. With this knowledge, our problem of computing minimum spanning tree reduces to the following. So the problem of computing a minimum spanning tree, that is MST, is to compute a minimum weight maximal independent set, for which we know an algorithm. So now we can write down our algorithm. And this algorithm is due to Kruskal. So first step is sort. Our given graph is G equal to V, E, and weight W. Sort E in non-decreasing order. Note that in this time we are trying to compute a minimum weight maximal independent set. So we have to pick the least weight edge first, which gives me E1, E2, E3, and then we set our A to be an empty set. And now for let's say there are m edges. So for I equal to 1 to m, do if A union EI belongs to script T, then and finally return this is our original algorithm. in this particular instance, this becomes the algorithm for computing an MST. But of course, we have this problem. We have to figure out how to test this, the membership of T. The criterion for this to be a member of T is that this should be cycle free. That is necessary and sufficient condition for this guy to be a member of T. Now let us try to see what does it involve. If you notice, the current A itself is a member of T, so this is an edge set which does not form a cycle in the graph currently. So A may look like the set of edges due to A may look like this. Now suppose a new edge EI comes. If this edge is running from one component to the other, then we can be sure that this is not going to create a cycle. The reason is there is no path from here to here. Hence, this edge, if there was a cycle, then there should have been a path from here to here. So as long as the two endpoints of EI are into different components, this is a safe bet. On the other hand, if the two endpoints of EI are in the same component, so for example this one, this, then we are sure that there will be a cycle. The reason is this is a connected component, so from the original set of edges there is a path from here to here, and then we have another edge we are incorporating, so that closes a cycle. So the necessary and sufficient condition for this test is that the two end vertices of EI must belong to two distinct components in the graph VA, where A is the current set of edges. This problem is the problem of union and find. What we will do is we will visualize the set of vertices in one component as a subset of as one of the subsets of a partition. So current set A defines a partition on V, vertex set. Each connected component is going to give me one subset, one set of the partition. These are the vertices in that set. The second one contains these two vertices, the third one contains these vertices, and so on. So we have to have a data structure which can store a partition of V, and when asked whether the given two vertices belong to the same partition or to different partitions, it should be able to find out the answer to that question. Once it finds out, suppose this is the new edge, it finds out that the two end vertices of EI belong to different partitions, then I will incorporate A into EI, and then this will become a member of A, and the new partition will be the result of clubbing these two parts. I will have to combine these two. So now we need a data structure. We need a data structure which stores subsets of V, namely V1, V2, Vk. These are the vertices corresponding to various parts of this partition. Their union is V, their intersection is empty because it's a partition. It can perform the union of two parts, can perform union of some pair of vertex sets, and further, given a vertex, it can identify which part that vertex belongs to, the membership in the two parts, and determines membership. These are the tasks that this data structure has to do. It should be able to store a partition, should be able to perform union of any pair, and then it should, given a vertex, it should be able to tell us which part does that vertex belong to. Okay, so now such data structures are meant for so-called union find problem. Union find. This particular problem is known as union find, performing union and determining the set to which a given vertex belongs. Union find data structure. So there are efficient data structures for this. I'll give you one example of which is not as efficient as another well-known data structure, but it's an easy to understand. So what we will do is, in this case, we will store each partition into a linked list. And so on. So here we have vertices of capital V1, here we have vertices of capital V2, and so on. When we have to perform union, all we have to do is connect an edge or a pointer from end of one to the start of the other. That's how we will be able to perform a union. Now we will do one more thing, that besides storing the vertex identity, so we have some vertex identity, we have vertex small vi1, vi2, vi3, and so on, i4. We will also store the identity of this set. So let's say the set identity is 3. It could be any single number. Set identity of this is, say, 5. This may be 7. So we need some supporting structures. What we will do is, we'll have one array with size mod of V. So this is vertex, this is for vertex 0, this is for vertex 1, vertex 2, and n minus 1. This will have a pointer to the node corresponding node in the linked list. So, this is say vertex V0, Vi4 is V0, maybe V1 is somewhere here and so on. So, we will store a pointer in this to the node of the corresponding vertex. In addition to this, we will have another array where we will have the same size and these will be the identifiers of the set. So, we have 1, 2, 3. So, this will be pointing to the start of linked list 3 corresponding to 3. Maybe this is 5. So, this will be pointing to 5 and so on. In addition, we will also save here the size of the list. So, for example, here we will store, so there are two parts, here is the pointer, here is the number of nodes in that list, over here it is 3 and so on. This is the information we will store in this data structure. So, initially what will happen is that all the vertices, because initially we have empty A, so each individual vertex will form a connected component, there are no edges inside it. Each linked list will contain only one element. If the element is, say the element is say 5, then we will also name its link, its set number is also 5, we will keep the same number. Each of these will be pointing to one linked list containing only one node, and initial cardinalities of the list will be 1. When we have to perform a union, we will first look at the two sets that we have to perform the union of. The two sizes that we have, we will pick the smaller one. We will walk through this, relabel this by the label of the larger one. So, suppose we have to perform the union of these two, the label of the larger one is 3, label of the smaller one is 5. We will walk through this, we will relabel them as 3, come to this point and then form a pointer from here to here. That way we will have now a single linked list containing all these elements. We will do the necessary bookkeeping here, we will set this to 0, set this pointer to null, and this pointer will be now pointing to this position. That way the union will be performed. It is very important to keep in mind that we will always relabel the smaller set or smaller linked list. Now, as far as find is concerned, if I want to find out which set does element 2 belong, I will say element 1 belongs, I will just go to the node and we will look at the set identity, which is this, and this will tell me which set does 1 belong to. It belongs to set identified with 7. So, these two operations can be performed in this data structure. When a new edge EI, which has two end vertices A and B, is to be incorporated in our set, we will check which set A belongs to and which set B belongs to. If they have the same identity, then we will drop it, because in that case it is going to form a cycle. If they belong to two different sets, then we will actually go to the corresponding sets, perform their union and update the data structure. This is all we have to do. Now, in this data structure, what is the cost of find and union? We are going to, for every edge, we are going to find the sets of the two vertices, and then we are going to perform unions if these are two distinct sets. Notice that in the process, this linked lists eventually, starting from singletons, they will eventually form a single list containing all the vertices, because we are going to form a spanning tree. Spanning tree has got all the vertices in one single component. So these linked lists will eventually grow into a single list. So the cumulative cost of the union we will identify separately, and as far as the cost of find is concerned, it's a unit cost for finding out the set to which A belongs and unit cost of finding out where B goes. So the total cost, the cost of find is order m. M is the number of edges, because for each edge we have to do constant amount of work. Cost of union we will find out cumulatively. The way we go about is as follows. Notice that the total cost of union is the total number of relabeling we perform. The reason is, when we perform union, we walk along the list and we go along by changing the label as well, and then finally we perform one unit cost, we incur one cost of forming this additional link. The cost therefore associated with this operation is the size of the smaller set plus a unit cost, which we will account for later on. Now what we will therefore do is, the cost of the union is the number of relabels performed on all the nodes. Now notice that a certain node goes through several relabeling as it gets unioned over a period of time. But every time when you relabel, it becomes a member of a larger set, and not only a larger set, but that new set will be at least twice as large as this set, because in this case, when we are unioning this with this, now this node is a member of a set of 7 vertices. So each time the cardinality of its set at least doubles, and hence the relabeling cannot happen more than log n times, because you cannot double it more than log n times. Now each node is relabeled log n times, so the cost of union will be order log n for each node, and there are n nodes, so it is n log n. This is the cost of relabeling. In addition, there is a constant amount of work we do for every union. But every time you do a union, you reduce one set from the partition. And initially we had n members in the partition, eventually it turns out to be 1, so we do an additional order n work, hence the total cost is order n log n for the union operation. Now let us recall that in this algorithm, this task costs us order m log m. This we have figured out, this thing costs us order m plus n log n. That is what the union and find cost. So the total cost of this, notice that log m is same as log n. The reason is m cannot be more than n square. So log m is 2 log n, which is order log n. Hence the total cost of the algorithm is order n plus m log n for the entire algorithm.